You know, the world we live in, it's rarely a simple yes or no, is it? It's filled with ambiguity, with maybes, with sort ofs. So the big question is, how do we teach our computers to get a handle on a world that isn't just black and white? Well, the answer lies in this really fascinating idea called fuzzy logic, a way of reasoning that actually embraces all those shades of gray. And believe it or not, this is not a new problem. Way back in 1923, the philosopher Bertrand Russell basically said, hey, this rigid classical logic we're all using, it's great for some perfect imaginary world, but it just falls apart when you try to use it on our messy, real one. To really get what he was talking about, let's think about a classic puzzle. Imagine a table. Now start removing one molecule at a time. After one molecule, it's still a table, right? Of course. But if you just keep going and going, eventually you're just left with a pile of molecules. So where's the line? At what exact single molecule did it suddenly stop being a table? The thing is, you can't point to one. There is no sharp line. The whole idea of table is, well, it's fuzzy. And that right there gets us to the heart of the matter, a real tale of two logics. On one side, you've got classical logic. This is the bedrock of most of our computers, right? It lives in a binary world of absolute true or absolute false, 1 or 0. That's it. But on the other side, you've got fuzzy logic, which totally throws that out and says, hey, what about degrees of truth? What about all the shades of gray in between? Okay, so to really appreciate fuzzy logic, we've got to go back a bit and look at the history of this whole dilemma, this world that was built on stark, clear opposites. And what's so wild is that even Aristotle, this is the father of the very binary logic that has dominated Western thought for centuries. Even he got this. He basically said that a truly smart person doesn't try to force perfect, exact answers onto things that are naturally messy and approximate. He knew that sometimes the best you can do, the truest you can be, is to just get close. All right, so if people were thinking about this problem way back then, what's the modern fix? This brings us to the case for imprecision and the person who finally cracked the code. So the big breakthrough finally happens in 1965, thanks to a professor named Lotfi Zadeh. He came up with something called fuzzy set theory, and the idea was revolutionary. Instead of an object being either totally in a set or totally out of it, Zadeh said, what if it could have partial membership? It could be maybe 20% in the set or 75%. He basically gave us the math to deal with vagueness. And you gotta understand, this wasn't just some abstract idea for philosophers to debate. No, fuzzy logic almost immediately became this incredibly powerful tool for engineers. It gave them a brand new way to design systems that could actually handle the messy, imprecise data you get from the real world, as you can see in foundational books just like this one. Okay, so how does this all work in practice? Let's dive in and really break down what it means to think in shades of gray. All right, the absolute core of fuzzy logic, the secret sauce, is something called a membership function. The easiest way to think about it is like a grading system. Instead of just pass or fail, it gives a score, usually between 0 and 1. It's a measure of how much something belongs to a category. So 0 means not at all, 1 means 100%, absolutely, and everything in between is, well, it's a shade of gray. Let's make this super clear with an example we all get, the concept of tall. Now, in classic, or what they call crisp logic, you draw a hard line in the sand. You might say, anyone over 6 feet is tall, period. That means someone who's 5 foot 11.9 inches is just not tall. It's like a light switch, on or off. But fuzzy logic is totally different. It uses a membership function, which is more like a dimmer switch. So a person who's, say, 7 feet tall, they have a membership of 1 in the set of tall people. Someone who's 6'1" has a really high membership, maybe 0.9. And a person who's 5 feet tall has a really low one, like 0.1. See, this is so much closer to how we actually think about a word like tall. Now, to really feel the power of this shift in thinking, let's use a cool analogy. Just imagine for a second that we have a tiny little universe, and inside it, there are only 3 objects. We'll call them x1, x2, and x3. Okay, so in the old school classical logic, if you wanted to find a set, you have to make a simple choice for each object. Is it in the set or is it out? Yes or no. We can actually visualize this on a cube. If x1 is in, we move to the 1 on its axis. If it's out, we stay at 0. You do that for all 3 objects, and you're always forced to land on one of the cube's corners. And how many corners does a cube have? Exactly 8. which means that in our tiny three-object universe, classical logic only gives us 8 distinct possible sets. That's it, from the empty set with nothing in it to the full set with everything in it. It's pretty rigid. But now, here comes fuzzy logic. This is the game changer, because membership isn't a yes-no choice anymore, it's a degree. You are no longer stuck on the corners. You can be anywhere inside the entire cube. So maybe your set is defined by the point where X1's membership is 0.2, X2's is 0.9, and X3's is 0.5. You're floating right there in the middle of the possibility space. So think about what just happened. We went from just 8 possible sets to a literally infinite number of possible sets. And this huge, massive expansion in what you can express, that's what lets fuzzy logic capture all the subtle details and complexities of the real world in a way that rigid, binary logic just can't touch. Okay, so when people hear this, a really common question pops up. They say, wait a minute, isn't this just a fancy word for probability? And the answer is a huge, definite no. And it's a really important difference to understand. So let's nail this down. Here's the difference in a nutshell. Probability is all about the likelihood that something will happen. It's about chance. Will it rain tomorrow? There's a 70% chance. Fuzziness, on the other hand, has nothing to do with chance. It's about the vagueness of the description itself. How cloudy is it? Well, it's kind of cloudy. They're just 2 totally different types of uncertainty. Let's use an example with a basketball player to make this crystal clear. Okay, step 1. A scout is told there's a 95% chance a prospect is over 7 feet tall. That's probability, right? It's about uncertainty. Once they measure the guy, that chance disappears. It becomes 100% or 0%. He either is or he isn't. The uncertainty is gone. But now, let's look at the fuzzy view. What if the scout is told the player has a 0.95 membership in the set of very tall people? That's fuzziness. Even if they measure him and he's 6'11", his high degree of tallness doesn't change. It's describing the attribute itself, not the chance of some binary outcome. Okay, so this is all really interesting theory, but why does it matter in the real world? Well, it turns out this ability to handle imprecision has completely changed the technology we use every single day. You might not know it, but fuzzy logic is the hidden brain working inside tons of devices you own. Think about your washing machine, for example. Instead of just being on or off, a fuzzy controller can sense if the clothes are kinda dirty or really dirty, and it adjusts the water and the cycle time perfectly. Or your camera's autofocus. It can understand if the image is mostly in focus or just a little blurry, so it can make those tiny, perfect adjustments. You'll also find it in things like anti-lock braking systems, your home's climate control, and even in super complex financial systems, making decisions with messy, incomplete data. So, when you boil it all down, what's the big takeaway? This leads us to the real power of being a little bit vague. Lofty Zeta himself, the guy who started it all, he summed up the entire philosophy in this one amazing sentence. He realized that our human ability to work with imprecise information, that's not a bug, it's a feature. It's our superpower. And by building that same strength into our machines, we just make them smarter, more powerful, and way more adaptable. And that really leaves us with a huge, fascinating question for the future. As we keep building more and more complex AI, maybe the biggest leaps forward won't come from making them faster or more precise calculators. Maybe, just maybe, the real breakthroughs will come when we teach them to be a little less rigid, a little more flexible, a little more human. What kind of problems could we solve then?